Okay, Watson, could you explain this purification process from A, B, C, D, E, F? So A here, English.
A element layer deposed on substrate as a hard mass.
So figure A. So which one is the? He said he deposited aluminum layer. So in this figure, which one is aluminum?
I see this one.
I mean figure A.
Figure A. This one, the blue one.
You are wrong. So they deposited oxide, metal, oxide, metal, oxide, metal, oxide, metal, oxide, metal, oxide, metal. So this is CMOS, the transistor over here. And we have metal 1, 2, 3, 4, 5, 6. We have 6 metals. And between metals, we have oxide. And the yellow one here are vias, the connection between metal layers to make them conduct. And in this step, they deposit metal 7 as a hard mask. Okay, so could you read B?
Photoresist coating and pattern for pad and bump area protection.
Okay, so in figure B, which one is the photoresist?
Photoresist is we grow this first and we
Photolithography.
Photolithography is
okay. So photoresist is a polymer. Then we just spin polymer on top of the wafer. Then we use our photomask because you are going to draw photomask. So we use the photomask here and with UV light, ultraviolet light to expose the polymer. When the polymer was exposed to UV light, its structure was damaged, become very weak. So after that, we put the wafer inside a chemical, like to put some chemical liquid, then the damaged photoresist will be dissolved into the chemical liquid. After that, we can use DI water to clean the wafer, then put them on top of the oven to dry the wafer. So you will see after the photolithography process, you will have this one, step B. So, okay, thank you. You can go back. So any question? So, any question? Ahwan, ask one question. Any question?
How to draw it?
How to dry it?
When
Draw the photo mask?
yes.
Yeah, we use software, Edit, Virtuoso, or K-Layout to draw the CAD software to draw the photo mask. You will learn that.
Okay.
Okay. Okay, stop. It's step 3. So could you read this one?
Deep reactivity ion entering to remove temperature and silly substrates.
Okay, your English improved. Okay, so could you explain step C? What happened?
It put this in here and it dip only this out.
So what?
Remove
So
here.
which part is the dielectric?
This part.
Yeah, the blue is the silicon dioxide dielectric. So first they use deep reactive ion etching. Go down to remove the dioxide because this photoresist and the aluminum here protect the material under them. And here and here and here, there are openings to the ion etching. So the ion will attack the dielectric till the silicon surface. Then step 2, they use silicon etchant to remove the silicon from this opening. From this opening, they just go in all directions. So they will go like this. So, Amin, do you understand? Okay, you can go back. And Amin, please come over here. Okay, we have 2 steps etching process. So for first step, which part is removed? First step, etching. Here or here?
Oh, here.
Okay. First step, etching. We remove. Then second step, etching. We remove the silicon. Then, because first step, etching is we have the ion has a direction. From top goes down. So see, from top goes down, so the etchant probably won't go sideways because the high-speed ion goes down, attack the dielectric this way. But the second step, the chemical etchant will go in all directions. So you will see the undercut here. Undercut here. Okay, thank you. So for mains structure, because you can think this is anchor. So here, if the anchor, at the bottom of the anchor, some silicon is removed, what will happen to, because this is mechanical structure, the mechanical structure is connected to the anchor. So if supposedly anchor should be strong, steady, but if some silicon is removed at the bottom, so what will happen to the connection of the mechanical structure to the anchor?
Maybe it will be disconnected because the high for the high edging.
Okay, so supposedly anchor should be strong and fixed. So when the mechanical main structure in motion, and the connection between the mechanical structure and the anchor. So at the interface is fixed. But if some material under the anchor is removed, so the interface between the moving structure and the anchor, so the interface now is not fixed. The interface will have some small motion. So this small motion will influence the behavior of the mechanical structure. Do you see that?
Yeah.
So if you do device simulation, you assume degree of freedom are all 0. But now, in reality, when they go to TSRI to test their accelerometer, the interface actually is not fixed. It will have some small motion between the moving structure and the anchor. And when you go to TSRI, did you start the testing from low G to high G, from 0, 1 G, 2 G, 3 G, or you start from 10 G? When you broke their device, is it you start from 1, 2, 3, then eventually you broke, or you started from 10G, from 1?
0.
So 1, 2, 3, fine. But 10G, okay. After we finish the etching, we remove the photoresist. Then imagine when we do wafer fabrication, the wafer has, the size of wafer is, say, 5.25 inches. It's a big wafer. And each mains device, for example, might be 1.5 millimeter times 1.5 millimeter. So you have many tiny mains device on the same wafer. But when you receive your chip, it is cut. So we put a cover to protect the mains device. Then we use a saw or a grinder to separate each die. So we can have many dies from the same wafer. So after that, you can either remove the cover and put them to a tape package for further testing. Ready? Okay, please.
So I think in figure C, so it's the sensor that suspend at the air. How to fix those two?
Remember, this is a cross section. So for example, if this is your solid, and see here, so you can imagine they have this. So if we cut, here, we use a scissor to cut. You can only see this part, and it's all empty. And you can see another solid part here. And if the interconnection is is here. So if you cut here, you can see all solid from left to right. But if you cut here, you can only see the solid here and here. So you won't see anything because they are air.
Oh, okay.
So because it depends on where you make the cut. So looks like when they cut this way, the connection part is missing. It's just the cross section, the cut.
Okay, understand.
Thank you. Okay, 1P6N process. So this is the process list. So we have, say, this is photo mask. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 photo mask. So you will draw 12 photo mask for this design process, main design process. So for the first one, number 39, you draw the contact, and 46, you draw the metal one. So previous page. So in order to make a device like this, you need to let the machine knows. So we have polysilicon here. So this is a transistor. We have polysilicon. We have metal, and polysilicon is the gate of the transistor. So between gate and metal one, we have some interconnection conductor. So poly, then contact. Contact layer is the via between metal one and polysilicon. So you need to draw the photo mask contact layer. Then the machine knows where to create this contact. Then metal one. You don't need to take care of the dielectric, because dielectric are everywhere. But you just need to tell the machine where you will have metal one, where you will have metal two, metal three, metal five, metal six. Okay. Next. See. 46, metal one. 47 is the via 1, 2, because 48 is metal 2. And if you draw 47, you will create via between metal 1 and metal 2. Then see, metal 3, 50. Then 49 is the via between metal 2 and metal 3. So finally, you have 56, metal 6, and you have via 55 between metal 6 and metal 5. Okay? So this is why we need 12 max. And here is the thickness. The thickness for the oxide. See, 2.06 is the thickness of metal 6. So can you go to previous? So this is metal 6. So metal 6, the thickness is 2.06. So you can imagine, before we do metal 6, it's all oxide. Then your photo mask will expose this area, this area, this area. Then you can do aluminum. You can. We will do that later. Okay, next page. Okay, next page. The color is not clear, but this is Metal 6 photo mask. When you use the computer CAD software, you will draw the pattern of Metal 6. Okay, next page. Okay, this is a 3D view of the mechanical structure. It's an accelerometer. Then this is Metal 6. Metal 6 and Metal 5, Metal 4, Metal 3, Metal 2, Metal 1. So the metal layers. And see, Metal 5, we have the aluminum wire. You can imagine this is an aluminum wire for signal flow. So we have, say, Vs plus, voltage in and voltage out. You can imagine. We have two signal lines. Then this signal line connected to Metal 5. This signal line connected to Metal 3 layer. And we have anchor here, so we don't need to draw anchor. So, I mean, we need to draw head data in the layout, but here we connect to the anchor. And here we connect to the anchor. And for this one, they are inside the silicon. For this one, inside the silicon. And here is free to move. So if there's an acceleration in this direction, because we have spring here, so you can, if this is a mass. We have, the mass is connected to the anchor through the spring. So another set will connect to the anchor. So if there's an acceleration in this way, then the structure will move back and forth. Okay, then here we have C. Okay, this one and this one. See, this one is metal, and this one is metal, and is it possible to zoom in here? Yeah, to zoom in. Okay, good. So imagine. So this one is connected to, so here, this part is inside the silicon, fixed, but here is free. Here is free. So, and this one is connected to the mass. So this one can move, and this one is fixed. So we have air between this metal and this metal, metal 5. So This is ground. This is Vs plus. So this one is a parallel capacitor. So we have a gap between the parallel capacitor. We have positive charge, ground, negative charge. So this one is a capacitor. Ami, do you understand? Okay. So the capacitance C equal to dielectric constant times the surface area divided by the gap. Then if there's an acceleration, so this shuttle mass move, so the gap, this gap becomes smaller. So because C equal to epsilon A divided by gap, so if the gap is smaller, the C is larger. C will be changed. Then the charge will flow. Then if the signal can be detected by your analog circuit. So this is the principle of accelerometer. And see, we have via. So this is metal 5, metal 5, metal 5, metal 4. And we have this via. The via between metal 6 and metal 5. The via between metal 5 and metal 4. So we have a via. So you can imagine the capacitor is from the top to the bottom. Because via is tungsten, it's also metal. So they are conductors. So the whole surface area actually are the capacitor surface area. If you don't draw the via, then here is only dielectric, silicon dioxide. There's no conductor here. So we need to draw conductor via to make the whole structure, the whole finger as a conductor. So this is the layout, the top view, a schematic of the device. So if this is the chip, now we put our eyes on top of the chip and look down. So this is the top view. Top view. So we have metal 6 for the spring and the mass. And we have metal 1, metal 2, metal 3, metal 5, metal 6 here. And here we have metal 1, 2, 3, 4, 5, 6. So we have the capacitor, many capacitors here. And we have one. So we have the dimension. So this is 8.8 times 8.8 hole, and hole between holes 7.2 micro. This is the size of the hole. Do you know why we need to have a lot of holes on the shuttle mass? Hugh.
In order to put the chemical down to have the reactive etching at the bottom, we need a hole, because many holes, and we put the chemical inside the hole, so the chemical go down, chemistry go down, and we have the undercut. Of the
Okay, can you go?
structure.
Yeah, can you go previous? Yes, this one. So imagine we have a shuttle mass very large. If you don't have the holes here, if you don't have the holes, if you don't have the hole here, so this is shuttle mass. We have a hole here, 8.8 times 8.8 micrometer. So again, if you don't have a hole here, what will happen? Come over here, please. Okay, if here you don't have opening, so you have aluminum or here, or aluminum. So what will happen? You don't have a hole here.
Here have no. These two is connect together.
Yeah, yes, certainly. But during the silicon etching, if you don't have a hole here, so what will happen?
We will connect here.
If you don't have a hole here,
Uh-huh.
then what will happen?
What will happen?
Yeah. What could happen?
Will maybe fix on here. And
Yes.
it cannot move.
Yeah, because if there's no hole here, when you do the etching from here and here, it'll take a long time. So eventually, maybe silicon, we still have silicon here, then this shuttle mass is fixed to the bottom. So this shuttle mass cannot move. Okay, thank you. Okay, next page. Remember a previous. Remember. And can you go to your K layout? Okay. So this one connect to the shuttle mass. This one connected to the shuttle mass. And this one connected to the wire, the signal line. So because this one is inside the silicon, so this part is fixed, cannot move. So these two connected to this signal line. So these two are also fixed, but this one can move. So we have capacitor 1, capacitor 2. So if this one moves, capacitance 1 increase, capacitance 2 decrease. Amin, come here. Now Amin like come over here. So when this device, when the shuttle move this way, the capacitance here increase or decrease?
Increase.
Okay. And the capacitance here increase or decrease?
Increase.
The capacitance here increase, a capacitance here. So which one increase, which one decrease? C1, C2. So which one, if this shuttle mass move this way?
Oh.
So C1, which one? C1, C2, which one increase?
C2.
C equal to epsilon A divided by G. G is the gap. So this is gap 1, gap 2. If the shuttle mass move this way, gap 1 decrease or increase? Gap 1. and gap 2. So if the shuttle mass move this way, gap 1 decrease or increase,
Decrease.
and gap 2
Increase.
increase. So gap 1 decrease. What happened to C1? Gap decrease. So C value C increase or decrease?
Increase.
Yes. And C2 increase or decrease?
Decrease.
Okay, thank you. So one capacitance decrease, the other one increase. Okay, go to the PPT. Okay, next page. See, if this one move this way, C1 increase, C2 decrease. So we have a lot of C1. So see, we have two. So we have one metal and one metal here. We have oxide at the center. One metal, one metal. Okay, next page. So see, this one. See, this one connected to the shuttle mass, and this one connect to the signal line. So here in signal line, one signal for C plus, one signal for C minus. So they use metal 3 for C plus signal. They use metal 5 for C minus signal, for example. So in this signal, metal 3 wire and metal 5 wire, they have their signals are different. So we use the metal to transfer signal. So Ahwan, do you understand? Okay. We have 1P6N. Each metal layer can be used to transfer signal. So you can have a lot of choices to make for your signal wiring. Okay. So this is spring. So we have spring. So for the spring design here, it's easy to move this way. And it's not easy to move this way because the spring, see, it's very easy to move this way. Then the total length, 815 micrometer. Total length. And this is the finger. And the upper finger, we have 41. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 41. And the lower electrode, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Keep going to 42. Okay? So this is 41, so this will be 42. Then the shuttle mass, the size 570 by 2550. So this is 250 micro. This is 570 micro for the shuttle mass. And the etching hole, 8.8 by 8.8. So the hole. And the gap, the distance between two holes, 7.2 micro. And for this one, they just use metal 6. for this long structure. See, it's a sandwich structure. Metal 1, 2, 3, 4, 5, 6. And we have polysilicon. And metal 1 and metal 2. Because when they do deposit the metal, they may have different pressure or temperature. So the material of metal 1, material metal 2, although they are aluminum, but they may be aluminum brothers. See, you are humans, but this human and this human are different, right? The same aluminum, they are all aluminums, but they are different aluminums. Metal 1, metal 2, different. Maybe one is stronger, the other one is weaker, okay? So when we finish fabrication, after we remove the dielectric and the silicon, then the structure won't stay straight because we have many layers, and each layer is different. So they may fight with each other. They don't like each other. Some metals like each other. Some metals don't like each other. Some metals will see the fabrication process, usually temperature will be 1000 degrees. So after we finish the fabrication, the temperature goes back to the room temperature. So remember, each layer is different. So each layer has different crystals, different size of their cells, different coefficient of thermal expansion. So when temperature goes down, you can imagine each layer shrink, but differently. Some layers want to shrink more. Some other layers want to shrink less. So they are fighting with each other. So the device won't stay straight. The device will look like a wave. Maybe looks like a wave, look like this, or wave look, because we have different stress inside the structure. Okay? So according to our experience, some structures, if you only have metal 6, you don't have metal 1, 2, 3, 4, 5, their device will maybe looks very flat. But if you have 1, 2, 3, 4, 5, 6, because you have too many metals, and each metal is different. So because too many metal layers, they may become curved. So sometimes people just use metal 6 for the spring, for the long structure. But some people may use different combinations. They may use metal 1, 2, and 5, 6. In this way, they may have very flat structure. But it's not always true, because each time the result is different. Maybe this time I use metal 6, the result is good. But next time I use metal 6, the result is not good. So it's not always true, but we need to have a lot of design experience. Then we will know which combination is the best. But say, for example, your friend may like cheesecake, but sometimes maybe This year you send your friend, you give your friend cheesecake, he is happy. Next year you give him the cheesecake, he is still happy. But 2 years from now, if you give him the cheesecake, he may not be happy. Because depends on his mood. The same with this fabrication service. TSRI cannot always produce the same product given the same parameters because the machine will get old. See, you have many machines. They cannot always function. Like when you were 10 years old, you can run. But when you were 70 years old, probably you cannot run anymore. The same with all the machine in TSRI or TSMC or UMC. The same. Okay, metal 5. One for C+, one for C-. So what time is it, please? The file this you can check is this file is in your Virtuoso, the file directory, because you need this one to draw mains device, and we use Xmanager, Xshell, and change your directory to this one. Then ICFE, and you will enter the terminal. Okay, technology file. See the layer number for each layer. Different layer with different layer number, and the layer numbers are the same. Virtuoso, edit, K-layout, they will use the same layer number, but the layer name, if you use K-layout, you just need to make sure your layer name, layer number is the same as Virtuoso, and you will be fine. Okay, next page. So here is the step. You can look at this later by yourself. Next. Technology. Next. So we need these several cells. Accelerometer, finger, plate, beam. So you will follow this. Then so they have Dagan and Watson can be your coach to help you to do this lab session. Okay, next. Okay, next. The grid depends on your mains design. You can change the size of the grid, spacing. Okay, next. Okay, next. And some draw keys. Next. Layer AB6, draw a beam. Okay, next. So just draw a simple beam. And use align the beam because see we have different cells, plate and finger. So in the end, we will put all of them together to form your accelerometer. So you start with the fingers, so follow the dimensions. You can use ruler and stretch to align. So the ruler command is good for you to use. I almost forgot all the commands. So, but if you use it a lot, you should remember all the commands. Next, create AB7 from AB6. Do you remember this?
Yes.
You remember this? Layer generation, create. Okay, next. Create cell, next. Draw plate, AB6. And they use rectangle command. Next. And draw etching holes. We have a lot of etching holes. 15 volts, 35 colors. Okay, next. And align holes. So this is 8.6. 8.6 and 8.6. So use the ruler to align. Okay. Create plate with holes. Okay, next. AB7. So AB7 is C. And we need AB7 in order to have mass device. Remember, when we do the etching, we need AB7 to protect the AB1 to AB6. So AB7 there, the plate with holes. Finger cell. So we have 10 micron from plate to this. And remember, this is C1, this is C2, and this one is the finger fixed to the signal line. This finger connected to the plate. Okay, next. VR5 and E5. Next. Finger cell. See, we have two. For this, you have C1 and C2. And because you have the IP, the accelerometer IP. So you can, because I give him the IP, GPS, the 1D accelerometer.
Yes.
So if you are not clear with the metal layer here, you can open that GTS file and look into their detailed structure there. Next. And the geometry, the dimensions. Create AB7. Next. Finger cell. Next. We use instance because as long as you create one set of fingers, you can copy this. You can use instance to create a lot of instances. 41 set. So column 41, column 1 to create 41 instances. Next. And shift plus F to show or to hide the instance, the content of instance. Okay, next. Just follow the step by step. Next. Okay, next. Finger or what? Next. 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 Because everyone has his way to create the same device. So this is one way to do that. But you can have your own way as long as you can get the device. It doesn't matter how you got it. Okay, next. Next. So accelerometer. So you just put finger plate beads together and to draw the accelerometer. Cell accelerometer. Next. Some detail. Next. So because this is upper head, you can mirror the upper head to form the lower head. This is center line, mirror. Next, then align upper left bead. So this one, align with these holes, the beads. See, align. Next, then align the lower bead. Next, right bead. Next, lower right. Next. Okay, so this is the finished accelerometer. Next, finger align. Next, finger O1, default GDS2 file. So today, you will draw this one and export GDS2 file. And what time is it?
2:52.
2:52. Okay, so